Thank you very much. Good morning, ladies and gentlemen. I'm very happy to be here at the conference and to make my tutorial. This is actually the first time I make a tutorial on this very topic, and it's something new, not just maybe for you, but also for me. And a few words about me. My name is Dmitry Ustalov. I'm a postdoctoral researcher at the Data and Web Science Group of the University of Mannheim, Germany. I study computational lexical semantics, crowdsourcing applications. My overall background is from the engineering and software engineering, primarily information systems. So I'm usually focused more on how the things can be implemented, how the things can actually work, rather than other aspects of scientific research. The slides presents the outline of my tutorial. We will focus 7 points. First, I will introduce what graph clustering is and why should we care for this topic. Then I will talk about a few very simple concepts from the graph theory, just a small recap. The primary content will be focused on clustering algorithms. I will focus on evaluation, how to evaluate clustering algorithms. I will show you a few case studies, then discuss some aspects of their application, and conclude with the final remarks. Natural language processing is a field that processes, analyzes, synthesizes phenomena of the natural language. And this is a very important field because people use language to speak, to communicate, and it's very interesting, it's very useful to develop systems that process this language. And as you can see, linguistic data apparently is apparently often represented as graphs, relationships, and other objects that are connected to each other. And the general goal of graph clustering is how to capture the knowledge hidden by the data implicitly, using only the structure of this data. And the key point of my tutorial is that graphs are a meaningful representation, and in this tutorial you'll learn how to extract this useful knowledge from natural language data. Here are a few applications of graph-based methods, including clustering. So graph clustering was used to address a lot of problems in lexical semantics, in speech recognition, in data merging, and so on. Also, you could also know about a few other graph-based approaches, which are quite famous. So the first one is PageRank, the original ranking algorithm used by Google. And the second, BabelNet, which is a large-scale, multilingual semantic network. It's created also using graph-based algorithms, but not clustering. So we focus on clustering aspects, and this will be our focus of interest. A small recap of graph theory. So graph theory is a mathematical field that studies graph, structures of graph, properties, and so on. And we'll need only a few concepts of this very well-developed theory. First, as you can remember, graph is a tuple of V and E, where V is a set of objects. They are called nodes or vertices, and edge is a binary relation on this set. So set E is a set of ordered or unordered pairs that define the actual connections between the nodes. Second, so graphs can be undirected. So they have no directions between the nodes, no arrows or directed. They can be pointed to each other. We'll focus mostly on undirected graphs. There are a few properties, like if you have an undirected graph, you can have at most this number of edges. If you have a directed graph, you have this number of edges. A graph can be weighted, so we can map each edge to a number. And we'll need a concept of neighborhood, is just basically a subgraph from G, from the graph, that contains only the neighbors of the target node without this node. And the second part, and the last part of the graph theory recap, is how to represent a graph and how to use a graph. So I think if you read some textbook or in your university you did some operations with graphs, you were focused mostly on adjacency matrix. Adjacency matrix is a matrix which represents the edges between the nodes. So you see this small graph of 6 nodes, and the adjacency matrix represents how these nodes are connected to each other. This graph is unordered, so it has no arcs, no directions. So this matrix is symmetric. In directed graphs, it's not the case. It's not true. It's not the only approach to represent a graph, because since these matrices tend to be sparse, because you have a lot of zeros, it's very computationally expensive, memory expensive in particular, to keep all those zeros in memory. So people came up with a few efficient formats to represent matrices. Apparently, this matrices represents graphs, and they improve memory spending greatly. So also a graph has nodes, and each node has a degree. A degree is the number of neighbors a node has. So for instance, this node, bank building, has the degree of 2, only 2 neighbors. The maximum degree, delta, is the largest degree in a graph. So in this case, it's 1, 2, 3, 1, 2, 3, 4, 5. Yeah, it's fine. It's not a mistake. And the last thing we need from the graph theory right now is the concept of successors. In case you have a directed graph, the successors is a subset of nodes, so it's just a set of nodes which are reachable from one node. For instance, if there's be an arrow, it will be a successor, and so on. And that's it. That's all you need to know from the graph theory to understand most concepts from this tutorial. Well, let's focus on the problem definition. Actually, the problem definition in clustering is very general. So given a graph, we would like to find a set cover for a set of nodes called C, clustering, which is nothing but a set of sets covering the set of nodes. Very simple. There are 2 kinds of graph clustering algorithms, in fact. The first class is called hard clustering algorithms. This kind of clustering algorithms make non-overlapping sets, non-overlapping clusters. It's useful in some cases. In other cases, you need overlapping clustering, and in natural language processing, you can think of the concept of ambiguity, when some word can have several meanings, and to address this, you probably need this soft clustering. So the overlapping is non-zero. Is non-zero. That's true. The most problematic part, and the most actually interesting part of the whole graph clustering concept, the whole graph clustering field, is that nobody knows what a good clustering is. And that's the challenge. And each algorithm defines what good clustering is. And basically, we can have only a very general information, like a very good clustering algorithm should put similar objects together and dissimilar objects not together to ones which are similar. And that's it. And at the slide, you can see an example of 2 kinds of clustering. The first, hard clustering, you see that one node belongs to one and only one cluster. In the second case of clustering, you can see that this node belongs to blue cluster, this belongs to like yellow, or what's the color. And this one belongs to both. So it's the gradient belongs that it belongs to both clusters. Okay, before we proceed to the cluster algorithms, I would like to tell you about the motivation. So, okay, we have defined the task, we have defined the we have some concepts, but why should we really care for this? And this is a very interesting thing, in fact, because if you look at this picture, you'll see some mess, okay? But this mess has a lot of sense, because in natural language, many phenomena tend to follow the same distribution between the languages. So there are a few observations, like, for instance, co-occurrence networks, the networks of word co-occurrences in a text tend to follow the Dragovtsov-Mendes distribution. It's a bimodal distribution. And semantic networks tend to follow a scale-free distribution. So it's like the power law of degree distribution and so on. And the answer for the question like, can we trust graphs? The answer is yes, we can. And in this case, so this picture, it's from the paper by Stivers et al. And they developed a model for semantic networks, and they found that, wow, we can predict the properties of a semantic network, and in case your graph clustering algorithm can capture these properties, you will get the more or less good results. In this tutorial, I will be focusing on 4 different graph clustering algorithms. The first one is called Chinese whispers. The second is Markov clustering. Both are very simple, fantastic algorithms which work very well. Both are hard clustering algorithms. And then I will go further to soft clustering algorithms like MaxMax and WhatsApp. In fact, it's not correct to say, oh, there are only 4 algorithms. Of course, it's not true. There are a lot of them, and you can find them on the internet, in the scientific literature, or you can come up with your own. I'll focus only on these 4. OK, Chinese whispers. It's a very simple algorithm. It is named after a famous children's game called Chinese Whispers, or Глухие телефоны in Russian. And it's very simple. So it's a randomized algorithm, which means that it tries to use randomization to achieve the goal of clustering. And in case you were studying graphs before, you can be aware of a very, very famous and a very, very classical algorithm but by Karger, which is called Karger-Mincut algorithm, which tries to do a graph cut using just randomization, and it works very well. And Chinese Whispers is not similar to it, but it uses randomization to do clustering. And it's so simple, it's so efficient, it's really a cool thing to say. And it was designed by Chris Beeman in 2006. It was focused on application to a few natural language processing tasks. The first is word sense induction, the second is language separation, etc. When I present algorithms, I will show you first the general overview of the algorithm, then I will present you the actually pseudocode. I try to maintain the same notation for the whole 4 algorithms I present. And finally, I will show you a demo of the algorithm. I really came up with some, in my opinion, really nice illustrations. I really want you to love them. And then I will discuss the properties of each algorithm. OK, let's go. We have a graph as an input, and as the output, we have a clustering. Actually, this part is virtually the same for all the algorithms you have. Chinese Whispers works as follows. For each node, it assigns a unique number. For instance, if you have 10 nodes, one node will be 1, second 2, and so on and so on. The order is not necessary, just these numbers need to be unique. Good? And that's almost done, actually. So now we do the following things. While labels change, so while we don't find that labels stop changing, we are doing the following thing. On each iteration in this while loop, we are passing through the set of nodes in random order. So every iteration here is actually a different shuffle of your set of nodes. And in each this internal iteration, so in this U loop, you do a very, very simple and straightforward operation. You say, now I change the label of my node. And to do that, I select, don't be afraid. It should not be afraid. It's just, notation. You pick the most weighted label in the neighborhood of U. There is a special function, weight. Basically, it can be just the number of classes, number of labels I appeared in the neighborhood. So you select the most voted label in your neighborhood, and that's it. Then, after you did this, the algorithm eventually converts. We'll talk a little bit about this later. You just transform labels into clusters, and that's it. Very simple algorithm. Just pick the labels, do some shuffling, and eventually it will provide you with the clusters. It was really weird, but before we go to the example, let's discuss the weighting functions. I was discussing a lot of this question with the authors of the algorithm, and they use usually 3 kinds of weighting functions. The first one is called, well, they refer to it as top, which means given a graph, actually given a neighborhood of U and the candidate label I, we assign to this label in this neighborhood the weight, which is equal to the sum of the weight, edge weights of this label in this neighborhood. There are 2 variations of this. First, the numerator is the same, and the denominator, the first is just the degree of that candidate node, and the logarithm of the same number, especially, of course, with 1 to prevent division by 0. That's it, very simple. Let's have a look at the example. So we have the following graph. This subgraph has 5 nodes. This subgraph has 6 nodes. And we will use Chinese whispers iteratively to cluster this graph. OK, we initialize the algorithm. We provide every node with a random label. I will use colors because it's very convenient to use colors to find out which clusters are which. We initialize the algorithm, and now we see that every node is provided with some number. Let's go. We need to select, so we process the graph, and we are starting to iterate over our graph using a shuffled order of nodes. So I picked a random node. Let's call this 4. For node 4, I see its neighborhood. It's like 2, 5, 3, 1. Yeah. And we, in this case, we don't have a weighted graph. Chinese whispers can be applied to both weighted and unweighted graphs. In this case, for the sake of simplicity, without any loss of generality, we use unweighted graph. So the weight of every edge is 1. And since this is true, let's compute the weights for the nodes in this neighborhood. 1, because there is only one blue node here. 1, 1, 1. So the colors, all the colors are different. We can pick any label we have here. For instance, it will be 5. Look, it updated here. Let's pick another node like this, 11. The same situation, actually. We have this, and etc. Let's pick this. Intuitively, it's not correct because, well, I expect this cluster to be of same color. I expect this cluster to be also the same color, which is desirable property, but don't worry, everything will be fine. Let's have a look at this. Change the label to this, for instance. Let's have a look at this, because we updated this one. We don't visit, during the one big iteration over all the nodes, we do not visit a node twice. So in case since we updated this from this label, we don't visit here, but we can visit this. And we actually should, because this is the algorithm. We should follow every step. We select this. And have a look at this neighborhood. Actually, there are a lot of options, actually. We can we select 2? No, because it's weight only 1. Can we select 3? No, because it's weight only 1. Can we select 11? You know the answer. Can we select this color? And the answer is yes, because we have 2 nodes in the neighborhood of this color. Wow, right? Another node, same situation. another node, the same situation as in the beginning. Let's pick this. Another node. So right now, have a look carefully. We have the same situation as here. We have the two nodes of the same color. Let's select. We must select. Let's go here. You know the answer. Let's go here. You know the answer. Let's go here. You must update it. Done. Let's go here. We have not been here yet, so it appeared only on this slide, on this iteration. OK? And actually, if you repeat the same operations once again, so you got the clustering, you got the algorithm converged, the labels are not updating, and without any information on the content, you just use the structure to infer clusters. And this answer, well, is correct. Intuitively correct, of course. Now the discussion on this algorithm. First, which is really cool in Chinese whispers, it's parameter-free. So it's non-parametric, and it's very simple. It takes at most big O of number of edges to converge, and it is very efficient for a lot of NLP tasks like word sense induction, language separation, whatever. It really works very well. Like any algorithm, it has a few disadvantages. The first one is it's randomized, and every run can be different. Because in case of a large graph, you can have some differences in order, and since the order is different every time, you have different results because some nodes influence the others in a very various extent. Another problem is node oscillation, and this is actually one of the most challenging problems in Chinese whispers, which is not addressed by the original algorithm. The problem is, in case, if you look here, suppose you have a node, this, right here. And suppose this node, is only here. So it can turn only this color or this color. And in case of very unfortunate set of events, you can be pretty sure that the algorithm will never stop working because this node will blink. It's like, oh, now 8, oh no, now it's 2. OK, now 8, now 2, 8. Very bad. And it's a very unfortunate property of this algorithm. You can actually overcome it by taking into account the counts, the frequencies of how each node, how often each node oscillated. But it's a crutch, it's a heuristic, and the general form of the algorithm doesn't presume this assumption. So oscillation is the thing you have to deal with. Generally, you have two ways. The first is frequency threshold. I think it's not really one. The second option, and usually when you see like the algorithm has no formal convergence guarantee, in Chinese whispers it's very true, you should instead use just the limit of number of iterations. Chinese whispers converge very quickly, so if you set maybe 8 iterations or 10 iterations, it should be enough. There are two implementations of Chinese whispers. The first is the official one. So Chris Beeman is now a professor at the University of Hamburg. They offer their official implementation in Java. I have written my own implementation in Python after this implementation, so it's simpler to use, I think, because Java is a more bloated language than Python, which is a scripted language. So for prototyping, you can use actually both, and I recommend you have a look at this because it's very simple, it's very efficient, and I think it's a lot of fun to use it. We have some examples and so on. So Chinese whispers is a very cool algorithm. I really like it. It's very simple, it's very efficient, and I was really impressed. Like, wow. You can just do randomization stuff, and this randomization stuff results in a very, very, very good results. You see the papers, you see the applications, and I was really impressed. But in fact, in the Chinese whispers paper, the author says that actually Chinese whispers can be treated as a special case of another algorithm called Markov clustering. a fantastic algorithm, absolutely fantastic algorithm. And this Markov clustering algorithm, when it comes to Chinese whispers, is something like you are doing one step of this algorithm a bit different. You take only one largest value when you do some matrix transformations, and you get virtually the same results as in Chinese whispers. So let's focus on Markov clustering. Usually when you hear the word Markov, which is the short name of one of the greatest mathematicians of the past century, you'll think, okay, it should be probabilistic now. It should be random now. But not random as Chinese whispers. It's stochastic. So it uses I don't know how it works, sorry. Is it cyberpunk? Pre-order now, please. Okay, so it's stochastic. So it uses matrices, it uses random walks, and these random walks are very natural way to express the relationships between nodes in a graph. So in fact, Markov clustering was developed by Stijn van Dongen during his PhD thesis in 2000. And this algorithm does nothing but it tries to simulate flows in a graph using random walks. Random walks is actually a wonderful property, it's a wonderful concept. And for instance, PageRank uses random walks with teleportations. And a lot of very cool algorithms also use random walks, and it's always impressive, it's always useful, it's always efficient. And Markov clustering algorithm has actually two primary steps. It requires the graph to be represented as an adjacency matrix, and this matrix is transformed using two steps. The first is called expansion, the second is inflation. Think of it like one expansion, you're just pushing your flow, and the inflation, you just get it out from every node. This series of transformations make it possible to get a hard clustering out of virtually nowhere again. And MCL has been applied a lot. Actually, it was not designed for natural language processing. It was designed mostly for bioinformatics stuff. I'm not expert in this field, so it was used primarily by the author for protein networks. I have no idea what it is. So they claim it to be useful. And in case you know the algorithm called affinity propagation, Markov clustering is similar, but some studies say it's better than affinity propagation. What's also interesting, when it comes to, for instance, in scikit-learn, you have the algorithm called affinity propagation, and it just transforms your input vectors into a graph, and then use affinity propagation. So maybe it's less computationally expensive, I can't remember precisely. So the idea is, you have a graph, you have an adjacency matrix, and you have two parameters. The first is called expansion parameter, the second is called inflation parameter. And usually you have clustering as the result. So first, this is the idea of the algorithm. I can't remember the proper explanation for this step, but the author says, do it, it works. And everybody does it, and it works. So you add a diagonal to the matrix, which means every node is looped by itself. Self-loops, basically. In case you have self-loops, it's OK, but the algorithm necessarily adds self-loops. It's an empirical observation, and you should take this into account. Then, there is a very common step, normalize. Don't be afraid of this notation. It's just for some sake of clarity. What it does, it takes a column of the matrix and makes its sum no more than 1 by dividing to the sum of this row, the sum of this column. Very simple operation, so just divide by the sum. And now it comes the loop. So until the algorithm converges, we are doing actually 3 operations. The first is called expansion. And it's nothing but the series of multiplication of the adjacency matrix by itself. Usually this parameter E is 2. So you just multiply this matrix A by itself using the general purpose matrix multiplication algorithms. Nothing really difficult. The second step is called inflation. And at this inflation step, you take every element of this matrix and you take R power of this element. So usually it's also 2, so you make a square of each element of the matrix. After taking squares, you do normalization. It's the same as here. So you just make it sure that the normalization applies, and you got the proper normalized values. As a result, you just see the clusters as ones in the resulting matrix after writing the algorithm, and you just gather them into a set of clusters, C. Okay, let's take the same graph, the very same graph we had before, and let's transform it into an adjacency matrix. This is a random example, so I will show you what happens to this matrix. So this matrix is symmetric. It has zeros right now. It has some structure here. Okay, so it can be one part. It has some structure here as well. It has some interconnections between them, and we are curious on how to isolate this. And using only these operations we have on the algorithm of MCL, Markov clustering, we'll get the clusters. So let's add self-loops, normalize, expand, so multiply by this matrix, inflate, expand, inflate, inflate, normalize, expand, inflate, normalize, expand, inflate, normalize, expand, inflate, normalize, expand, inflate, normalize. Nothing happens right now, right? Boring, very boring algorithm. Nothing happens, total disaster. But let's wait. Expand, inflate, normalize, expand, inflate, normalize. Oh, wow. I see something. Expand, inflate, normalize. Wow. Expand, inflate, normalize. Expand, inflate, normalize. Wow. Clusters. I have no idea how it works. Funny things aside, eventually the algorithm converts, but the author says, I have no proof. I have no idea how it works, but I think in case you're good at math, so I'm an engineer, I'm doing mostly engineering stuff, but in scientific research, so I'm focused on this. In case you are very like math, you can try to make a proof. I think one of the points is that since you are doing normalization, you are redistributing these weights, and since you constantly decrease the numbers during the inflation step, you also get this. Numbers higher. But why it tends to converge to these ones? I love this magic. So it works very well too. It was designed for protein networks. Markov clustering algorithm works very well in a lot of NLP tasks. It was, and it is, super popular. It has downsides. Change process is very fast, so you just can make a few iterations and it will eventually converge. MCL is not that good at running time. In fact, the running time of the Markov clustering algorithm, in worst case, is the cubic to the number of vertices. And for instance, if you have a graph of 1 million nodes, it would take long. But I need to be honest with you, because this algorithm and the author of this algorithm says the worst case is not that frequent, because in case you have an efficient sparse matrices implementation, and in case you have some pruning for very small values, you can speed up the algorithm substantially, but you need to know how to use or how to run sparse matrices. The author has an official implementation of this algorithm under the GPL2 license. It works very well. It's written in C, it's very fast, it's multi-threaded, very well. One moment. So I will upload the slides somewhere today, and maybe on the website there will be a link. So you don't need to make photos because everything will be on the website. So we have considered two algorithms so far, but the primary problem of these algorithms is not the problem of them, it's the property of them. They are hard clustering algorithms. We don't need hard clustering as NLP actually. No, that's not true. We need it of course, but sometimes we need something else. And this something else happened in this case. Look, suppose you have this graph, it's like some maybe relatedness graph, maybe some co-occurrence, never mind. And you have the node bank. And the node bank is ambiguous, is polysemous. If you run some clustering algorithm, like MCL or Chinese whispers, you will be sure that this item will probably be either in this cluster or in this. Sometimes also MCL can isolate it, which is also not that expected. You need these soft clusters. And to do that, we need soft clustering algorithms, because hard clustering algorithms will consider these types of graphs incorrectly. And I will show you two algorithms. The first is called MaxMax. I was really trying hard to find pictures, so it's like Mad Max, but MaxMax. Also, I was thinking to put here the photo of the TV show Maxim, but I think it's like copyrighted. Fantastic humor show. Yeah. And so MaxMax is a soft clustering algorithm which is very fast as Chinese whispers. It works. It's primarily designed only for co-occurrence graphs by Hoppe and Köhler in 2015. Oh, sorry, 13. Okay, a few years ago. And it works differently to Chinese whispers and Markov clustering, because it transforms the input graph, which must be weighted, into an unweighted directed graph. This directed graph, G prime, is a representation, and by definition, it's called quasi-strongly connected. And this algorithm does two things. First, it tries to represent the input graph as a directed representation, and it uses this representation to capture the overlapping clusters. Let's see how it works. You have weights, you have like graph, as the output, of course, you have clustering. Let's have a look. First, so this graph G prime that we will construct has the same set of vertices as the original graph, V, and it defines an asymmetric relation over V. It's called E prime. And as the first step, it does the following thing. For every edge in the input graph, U and V, if in this edge the weight of this edge for U is the maximal in its neighborhood, then add a reverse edge to the E prime set. So it reduces the number of edges, and the number of edges in E prime is smaller than in the original graph. So that's the reason, that's the idea, and that's how it works. Then construct a graph and make the following thing. We have some representation of the input graph. You'll see it on the screen a bit later, and this representation is very nice in the example. Now, since we have already constructed this graphical representation, we are trying to extract the clusters. For that, we mark every node as root and use the breadth first search algorithm or any graph traversing algorithm just to mark all the successors of node as non-roots. So we have roots, we have non-roots, and they say, okay, in case you have these root trees overlapped, you have overlapping clusters. And now you record the clusters as the result. Let's have a look at the example. There's a graph. It has 1, 2, 3, 4, 5, 6, 7 nodes. It has some weights. I hope I made no mistake. Let's initialize. Affinity is the set of the nodes for the given node, which weight is maximum in its neighborhood. Let's traverse the graph. Have a look at this neighborhood of R. You have this. Okay, everything's highlighted. You must be better at reading. And you say that S has weight 3, this has weight 2, and we must say it's S. For S, we found R. For T, we have 2 nodes actually. So it's 2 and 2. Same situation. So you get these affinities. These affinities represent something that we will construct right now. So we now need to create a new graph which has no weights, but it has arrows. And these arrows are reversal. You connect this to this, this to this, etc. Let's do it. So we connect this to this, this to this, this. I think this is the last one. Or, no, yeah. Now look, it can be bidirectional. We constructed this representation, and do you see something interesting? Because there is absolutely something interesting. If you go from here through all the successors, you will be stuck here. You cannot reach this node from R. You can't reach W from R because its latest successor, its closest, is T. The same thing comes to X. So intuitively, the clustering is like this. And this is what MaxMax tries to capture. So now mark everything as root, then select some node, mark its successor as non-roots, and the successors, the successors of X are also non-roots. And now we found this. So we traverse using breadth-first search to find the clusters, and eventually we get this. So this gradient means that it belongs both to these clusters. And here is our cluster, here is our cluster. You can see the labels. I hope there is no mistake, no misprint. I think it should be fine. And that's it, the MaxMax algorithm. What is cool about MaxMax is that it's non-parametric again. You just pass the graph and does everything for you. Very convenient, very simple. Its computational complexity is theoretically the same as Chinese whispers, but in practice, what is really cool, at least my implementation was even faster than my implementation of Chinese whispers. The theoretical complexity is the same, but this algorithm is even faster. However, it does soft clustering. It works very well on word sense induction. It was actually primarily designed for word sense induction, and the authors claim that it fits this task very well. It has a few downsides. The first one is actually I have no idea what the assumptions are in the core of the algorithms. Because in case of MCL, you have, okay, random walks. It will eventually converge to some stable state, stationary state, and in the state you'll have these clusters, and they are motivated by random walks. I understand this assumption. Chinese whispers say we are almost like MCL, but a bit more rough, which is also clear. But this algorithm, I have no idea what are the assumptions behind it. And what is funny is that when we were trying to apply it, I checked our implementation for a few times to the paper, which presents this algorithm. It was not working very well in our cases. So we tried a few algorithms, a few tasks, and they are not coherence networks, maybe because of this, no idea. So the applicability seems to be very limited. You can look our paper, it really doesn't work very well. And the authors provided no implementation in open source or either some binary files, which is a pity because I tried to did my best when I was trying this, when I was implementing this, and so on. I would like, nevertheless, to have some reference to say, okay, I'm correct or not, but I'm pretty sure I'm correct. But let's have a look at the different aspects of this problem. So let's have a look at this graph again. And let's have a look in the past. So a lot of years ago, well, there is a general problem in NLP called word sense induction. It's inductional kitchen appliance. Word sense induction is a task when you have either a text corpus or something else, and you are trying to come up automatically with a set of word senses for each word in this language resource. And Dorrell and Widows, a lot of years ago, in the beginning of 2000s, came up with a very cool and very nice approach for word sense induction using graphs. They used coherence networks again, and they say, okay, suppose you have a node neighborhood. So node neighborhood, you have this node and you have its neighbors. And what if we remove this target node? So you are trying to come up with the senses of this word. And given this graph, it's intuitively, you feel intuitively that there are two senses. One is bank has like some river part. Another sense is like building. And that's what they propose. Remove the target node, run clustering. They use MCL. And every cluster should be taken as the context of the if sense of the node. So this is the context of first sense of bank. This is the second one. Pretty simple. And when I was really impressed by this because this approach is very simple. It seems to be quite efficient. And during my experiments, I came up, now I will talk finally about my algorithm, with another graph clustering algorithm for soft clustering. And it's called WATSED. And the funniest thing about WATSED that it is not a clustering algorithm. So what is WATSED? WATSED is instead a meta algorithm, meta algorithm, which doesn't do clustering. Instead of clustering, it constructs another representation of the input graph. And in this representation, you can reuse the existing hard clustering algorithms, the very efficient, the very clever algorithms, to get soft clustering out of nothing. And we first published this at ACL 2017. And it does a transformation of the input graph. It replaces nodes by senses of these nodes. It does nothing, but it combines word sense induction approach, I described it one slide ago, with some removal, and context disambiguation, because you need to establish edges which are the subject for disambiguation. So you need to know which edge connect which sense of the word. And unlike MaxMax, which transforms edges, WATSED transforms vertices. The algorithm will be quite long, but I hope you will get this on the example. So it has a lot of parameters, but have a look at them. You have the graph. You have two algorithms. The first is run when you do word sense induction. It's called cluster global local. When all these senses are induced, you construct the sense graph, this representation, and you cluster this representation using another hard clustering algorithm. And basically, all you need to do is to remove the sense labels, and you get the soft clustering. That's a very simple idea. You need the similarity measures between contexts, and actually, that's it. You got the clusters out as a result. So for each node, you say, now I will be doing sense induction of each word U. You gather the neighborhood without this node, you cluster it, and you say the context. So the clustering of U is a set of contexts of sense of this word, and let's add the sense number to the global dictionary there. And so, okay, we just transformed all the nodes. So we just get the senses for each node. The problem is we have edges, and these edges are established between words. You don't know which sense is represented by each edge. So we need to do some transformations with the edges. However, the number of edges doesn't change. It works as follows. You need to disintegrate all the contexts. You take every word in the context of you. You head is a sense of you. So you are traversing through all the senses. You are taking each context of each sense, and you're trying to maximize this very weird expression. It works as follows. You're trying to find the optimal, well, the maximal. The sense of the element of the context, which similarity is maximum, and you compute the similarity between the context of this you had with you together. It's an important thing because we initially excluded the node from the neighborhood, and to the candidate context. So now instead of just having contexts like bank, riverbank, whatever, you have numbers, you have sense identifiers. And having these sense identifiers obtained, you just construct a set of edges for this sense graph. You construct the graph, you run the global cluster algorithm, you remove the sense labels, and you got the clusters. Let's look at the example. Suppose you have this graph. The problem is you need to have all the neighborhoods, and I cannot put the whole graph here. Suppose that building is connected to something else, and it's, well, actually in the middle of something. I'll show you only a localized example, but you will probably get the idea. I hope so. If you don't, let me know. I will redo it for the next time. Suppose you have input, you initialize the algorithm, you remove the word bank, you run clustering, and now you say, okay, I got two clusters, let's record them. You say, yeah, I have two clusters of bank, bank 1 and bank 2. You don't know actually the sense identifiers of them because these nodes can be, maybe I should get closer. These nodes need to be disintegrated because you don't know which sense of this word, this word, this word, this word are actually connected with this particular sense of bank. So that's the idea. Let's use the information. So having run this thing, this operation for sense induction for all the nodes in the input graph, you'll get a context for every sense of every node. For instance, you are trying to disintegrate this word building. So we have already, so it was question mark, not unknown. Now we have two. And we are comparing the context of bank 2, like this, to every context of every sense of the word building. And we eventually found, suppose you have two of them, edifies and actually the same. And we found that the similarity of this context to this is eventually higher than to this. We use cosine similarity, but you can use anything else like Jacquard similarity, whatever. Since this is higher, you must assign this number. The same operations is performed to every node we have. Now we got sense graph. It's totally disintegrated, and you have this wonderful sense-aware relationship between every node in this graph. And what is wonderful as well, you don't lose the edge-weight information because the edges don't change. You change only the start and end points of them. The edges don't change. You run the clustering algorithm. Wow, it makes it possible to capture these relationships. And now all you need to do is just to remove the sense labels. That's it. Very simple, very efficient in our experiments. But it requires some guessing of the algorithm, so you need to run either Chinese whispers or MCL, and you need some tuning. That's a disadvantage. Everything has disadvantages, you know. Good. Now, discussion on WhatSet. Of course, I'm biased because I'm the author of this algorithm. But I think one of the wonderful properties of WhatSet, it's actually conceptually very simple. When you run it, it scales very well. I mean scale, but by multi-threading, multi-processing stuff, it scales really well. And it shows very good results in very different tasks. So you can apply it not just for words. You can use, for instance, triples. You can use maybe some social network profiles, whatever. And I expect WhatsApp to work well. There are disadvantages. First, it's slow. Because in worst case, in case you have a complete graph, the computational complexity is the 4th power of the maximum degree. And it's really slow because of this disambiguation procedure. Even if you use a parallel implementation, which I offer actually, it's multi-threaded. I think, yeah, both are multi-threaded. The first one is in Python, the second one is in Java. Even in this multi-threaded scenario, it can take a lot of time when you have a very, a click graph, whatever. And it is as good as the underlying clustering algorithms are good. And very curious participants can ask me like, okay, but why do we need these clustering algorithms in case you just run in a clustering algorithm? It's an overkill because you have already disjoint graph. Okay, so it's one component, it's another component. In some cases, you can run like connected components, search algorithms, but it doesn't make sense in real graphs because you have maybe some connections over there. And as the result, the whole graph will be the same cluster, which is not desirable. So, and WhatSet is open source. You can use any of the implementations. I think this one is simpler to use. And as a little bonus, WhatSet implementation, since it's a meta algorithm, it requires all the algorithms to be executed. I implemented Chinese whispers, MCL, and MaxMax in the same API. Please use it. I hope it will be a lot of fun. And let's go to the more complicated topic, the evaluation. To evaluate clustering algorithms, we need to come up with some measures. And these measures are actually non-obvious. Because if you have, for instance, a supervised machine learning task, you can evaluate it more or less in a very straightforward way. You can compute, you have the gold standard data set, and this gold standard data set can be very simply compared. So you can compute accuracy, whatever, because you have classes. In this case, you don't have gold classes. You have some objects which are grouped together. We have something, and you nevertheless need to make it possible to find the gold clustering and to quantify the quality of your work. And for evaluating hard clustering, it's possible to use like the classic algorithm, rent index, whatever. They're all described in Manning, the classical Introduction to Information Retrieval book. But soft clustering is difficult. It's difficult to run. It's difficult to evaluate as well. And I'll focus 2 different measures for that. There are a lot of them actually, but these 2 I think are the most interpretable and straightforward. So the larger this measure is, the better your clustering is as well. And what is funny is that I was at ACL 2018 this year in Melbourne, and it was a very interesting discussion actually on the problem like NLP researchers. It's ACL, like A-star conference, the top of the top in this community. And there was a talk like people do not care for statistical significance. So for instance, if you have a difference like 0.001, and people claim our method is now state of the art, which is not true, because you must evaluate this, and we'll focus on this for a little bit. Okay, now, the first kind of evaluation measures is called paired precision recall and F-score. It's very simple. If you have a cluster, you can treat every cluster, which is a set of objects, as a complete graph. So it's a graph and everything is connected to everything. You can, by definition, have this number of edges in this graph, and you actually have. And you can just extract this number of these edges into a set of pairs. These pairs are unordered. Yeah, sorry. And Yes, two positives is the intersection. Yeah. Now it's, yeah, so when we make a, so it's only for one cluster named I. If you make a union of these clusters, you have P. Like you take the pairs for all the clusters, you have P. You do this for both your cluster in C and for the gold standard cluster in CG. That's why it's here, not here, because of the consistency reasons. And you take this pair union of P of your clusters, you do the same for the gold clustering. You simply compute the number of matches between pairs. Then you compute similarly, well, it's quite classical, right? The number of false positives, number of false negatives. You compute precision recall F-score. And this is very straightforward. It can be applied both to hard clustering and soft clustering, but the problem is it doesn't necessarily evaluate the goodness of soft clustering because it's implicit. However, it's a proxy to the results. Another measure proposed by Kawahara in 2014 is called normalized modified purity for soft clustering. By definition, purity, as you can see in the book, in the textbook, is the measure of how many items in each cluster are in the most belong to the dominating class of the items in this cluster. So in case you have a cluster of the same objects of the same class, you have the purity of one, otherwise it's not. And they generalize this notion by doing this. This notation is crazy, right? Don't read it. The idea is, it says, let's compute purity as the precision and recall. And the first is called normalized modified purity. It works as follows. You take every cluster of non-1 size. So everything that is size 1 is treated as incorrectly recognized. That's their idea, because it's a challenging problem. Very simple and maybe naive solution, but nevertheless. And then they, instead of just comparing the intersections, they are doing this weighted intersections, because you can have objects which appear in multiple clusters, and for that they introduced a very simple like weight computation function delta, and that's it. Actually, having computed these things, you get F-score and so on. What is funny is that we are in the WATSET implementation in Java, we also implemented this, and you can use this freely. I added this slide only, I think, a few days ago because I found this really important topic to discuss. How much time do we have? Fine. It's not enough to just say, okay, my results are better, I got some brilliant results, I got some numbers. Nobody cares for the numbers. The thing people care is the motivation of this result, so the explanation why it works, and one of the confirmations why it works can be the statistical significance of your results. And that's a very big problem in NLP because actually people don't care for that. The reviewers don't require it. People don't even know how to do it sometimes. Very bad. We need to be better than this. And for that, I recommend you to do the following. There is a very well-known paper. And so when we were discussing this problem with my colleagues in University of Mannheim, they say, oh, you know, every 10 years, somebody goes to ESL and says, please care for statistical significance, and nobody cares still so far. Let's go back to roots, to year 2000. And there is a very simple idea. For precision recall, F-score, accuracy, whatever, you can use a non-parametric randomized test. There's too much random things in my tutorial. And it tests the following null hypothesis. If you take the results of two algorithms, what happens if there are some same results and some results which are different? And what if you keep the same results assigned to each algorithm and you swap the different results in a random order? You repeat this for a lot of time. It's called computationally intensive. So you do a lot of permutations. And what is the probability under this null hypothesis so that we swapped the results by the algorithms, assuming they are equal, and what is the probability of it's true under this null hypothesis? That's the idea. It's implemented in this toolkit. It's also very simple, actually, but let's have a look. at the algorithm for instance, average values, which are accuracy and so on. It can be virtually trivially generalized to F-score, etc. You need two vectors, A and B, and the number of iterations, and this is the number of trials. And let's get the two-tailed p-value. So you can compare this p-value to some threshold called significance level, and if it's lower than the significance level, you can say, wow, my results are significant. That's it. First, let's find uncommon elements and record these indices. Well, okay. Let's count the number of cases when the results were the same under the null hypothesis. Let's go and iterate. So in each iteration, we will copy the original vector. And for each uncommon element, we will flip a coin, and shuffle the elements if we have, for instance, tails or heads. Never mind. If the difference between the original result is lower or equal to the swapped result, we can count this as, wow, no actual difference is found, because in case this expression if expression is true, we know that, wow, null hypothesis works because we swapped the results, but nothing substantial was found. That's the idea. You return just the number of S divided by the number of trials. This is the p-value. And in case you consider the example, let's have a look at the example. You have two vectors, 7 elements. You have only one common element at this position. So you have uncommon elements of this. Let's compute the mean values. It's like this, and the difference is 2. If you run 10 power 6 iterations, trials, you'll get this p-value. And under the significance level of 0.05, which is a pretty common one, you can say, wow, the difference is significant. And you can generalize this approach to a lot of other measures, and it has no assumptions behind, like normal distribution, whatever. It really has no assumptions. It's awesome to have such a test. Please use it. We don't have much time, but I'll try to make it quick. So, two applications of clustering algorithms. They are described in a computational logistics journal paper we submitted recently in August. The first is called scene-set induction. The second is frame induction. The first is scene-set induction. So, you know WordNet. You know, WordNet is a lexical database that has scene-sets, set of synonyms, and in WordNets, sets of synonyms are connected to each other using, for instance, hypernymy relationship like cat, animal, whatever. It's a very interesting task to create WordNets automatically, and I was really involved in this for a lot of time, and I really love this task. I came up with the WhatSet algorithm when I was thinking about this a lot, and let's have a look how to do this with graphs. So let's take synonymy dictionaries, like maybe, like, I can't remember the example right now, but let's go look. For instance, program. It's a set of pairs like program, and so on. Let's construct a graph using these synonymy pairs. Let's use word-to-vec embeddings to compute this cosine similarity between these pairs, so you get edges. And let's cluster this graph and treat clusters as these scene-sets. The implementations here, wow! And WhatSet outperformed all the other algorithms, and it was consistent. So you can discuss the result maybe later, because some algorithms worked no worse than WhatSet. For instance, MCL showed awesome results, but it tries to isolate the ambiguous nodes, which is undesirable. Max was very unstable because of very strange assumptions. So WhatSet showed the best results. And here is the example of these scene-sets from the English dictionary. They look really, really good. The second example is frame induction. I think everybody knows WordNet, but it's not the only, semantic resource the humanity came up with. Here is also a FrameNet, and the idea is you can describe frames. Frame is like a kind of structure which shows roles. For instance, you have a role like kidnapping, and you have those who are the person to be kidnapped, like the victim. It can be this words. You have perpetrator, it's the kidnapper, and the frame evoking element is like the primary element that corresponds to this kind of activity. It can be verb, it can be not a verb. Here it is. Frames are used in question answering and a lot of applications actually. We are curious of what happens if we use only syntactic triples, subject-word objects like cat, walk, maybe street, to induce frames automatically. Here is the idea. Here is the frame net. So it's just some sentences annotated with these rows. Very, very straightforward. It's a great work in Berkeley. People did this for a few dozen years. Very good results. Okay, so we have a triple. We map this triple in a low-dimensional vector space by concatenating embedding vectors. We construct a graph using nearest neighbors. Here's the graph. Each node is a triple, and we use graph clustering algorithms to aggregate the frames, and that's it. So we get 3 frames, like subjects, verbs, and objects. And here's the comparison with the state-of-the-art, like the higher skipgram. It's a tensor factorization-based model, which works really well, but our approach showed generally better results. So yeah, LDA frames also worked worse. Here are the examples of good frames, like company, supply something. It's automatically unsupervised. We got frames out of nowhere, which, in my opinion, is very cool. Here are the bad examples, of course. So this is terrible, this is terrible, this is also terrible. You see a lot of words here. Sad. A quick guide what to do if you want to do graph clustering. First, if you need hard clustering, do Markov clustering. It's an awesome algorithm, it's very efficient. If your graph is very big and Markov clustering works a lot of time, Chinese whispers. It's super fast. In case you need soft clustering, so what's it? Max is, I think, concurrent graphs specific. In case you have only vectors, you can represent your graph. Yeah, no, thank you. I'm almost there. In case you have a graph, you can represent your vector space as graph using 3 strategies. First, use k nearest neighbors of each vector. For instance, you can use Facebook's face library. It's awesome. You can use the epsilon radius of each vector, and you can, if you're a crazy person, I haven't seen this in real life, but it's in the tutorial I've seen on spectral clustering. So you can use a fully connected weighted graph. So everything's connected to everything, and you have weights. And think of a graph as a discretized vector space. I think it's one of the latest slides I have. There are some events. So the primary event specific for graph and based NLP is text graphs. It's usually collocated with ACL in the same dates. There are a few books, a few data sets. You can find a lot of useful information on NLPub on the internet. And I think to conclude, I would like to say, okay, graph is a very meaningful representation that has data, and all you need to do is to get this data from the graph. It's implicit. Graph clustering makes it possible to capture these implicit properties. The second is, these algorithms work very well. You don't need to do anything but running them. It's very convenient. I cannot be very, well, my coverage is not very large, so I have only 90 minutes. In fact, we had less because of these delays. I didn't cover spectral clustering. It's an awesome field of work. I don't understand it at all, but it's based on eigenvalues, and these eigenvalues correspond to clusters after some transformations. And there is a lot of work of community detection in large networks, like human networks. They are not very applied in NLP. So, in case you are interested in graph-based NLP, there are 2 prominent research directions I recommend you to pay attention to. The first is graph convolutional networks. The second is graph embeddings. So you can read these papers. They are really good. So thank you very much. That's it.
Questions, please?
Yeah, please.
Could you turn to the slide with different data we went Russian.net, Yarn, so.
Yeah. Yes.
Why the quality on Google.net is so much lower than on Yarn? It depends on the.
it's a very interesting question, actually. So let me explain these graphs again. There are 4 experiments. The 2 on the left are on the English language. The 2 on the right are on the Russian language. And this is the name of gold standard for each corresponding language. We found a substantial difference between the results of RuWordNet and Yarn because they are constructed by different principles. So RuWordNet is a semi-automatic translation into a WordNet-like structure of the root test Thesaurus by Natalia Lukashevich. And Yarn was a crowdsourcing initiative, and the coverage of synsets and the structure of synsets are different. So the results are really different. We did already, at the very same paper, an experiment. We tried to evaluate one gold standard on another, so it's like cross-resource. And they perform poorly on each other, so they are different resources. And the numbers are also different. More questions? Okay, I'm glad I finished this in time, actually. Thank you very much for your attention, and have a nice day.